In the class, you get like 6 to 8 people that show up while I'm talking. Oh, there's 2 of them right now, 3 of them. All right, let's get started. We just keep falling further and further behind. I don't know why. This is the 3rd time I've taught this class, but I don't know if I just talk slower to you guys because I feel like you're not getting it. I don't know. But I'm trying. Not a big deal, but we're going to just continue to forge ahead. All right, we'll see how it ends up at the end of the semester. I might end up just pulling some things out, which is fine. But hopefully we'll try and speed up a little bit. But don't feel like you need to stop asking questions either, okay? So ask questions if you need to. Let's see here. I was going to say that homework is due end of day tomorrow, right? Quiz is available right now if you wanted to go out there and take it, right? You have an hour to take it. And you have today through Friday to go out there and take that. I'm going to assign another homework after today's lecture. It'll be due Thursday next week. We will, pretty much after today, you'll have everything you need to do that homework, besides a couple things which hopefully we'll touch on Monday. What else? People been taking advantage of the EM Learning Center? Yes? No? Yes? Been good? Good. Don't forget that that's out there. I'm here, right? Daruk, who grades your homeworks, right? If you have issues with that, feel free to reach out to myself or Daruk, and we can get those cleared up as well, all right? So on Monday, we went through this example which helped us relate, right, power in shafts in particular for this class, right? Power in circular shafts. How that power can be distributed both via gear ratios, right, and different shaft dimensions and sizes, and how that power that is provided into a system, right, is the torque times a rotational speed, right? And that torque can be a function of, in our case, we were given a maximum shear stress that the shafts, right, the shafts in our system can handle. And so that's kind of our governing limit, right? That's limiting how much power we could put into this, or in this case, how much speed, because we were given an amount of power that we were putting into the system, okay? So we worked through that to figure out, okay, what is the speed of the motor required in order to not overcome the ability for our shafts to resist that torque, right? So we went through that. Now we're going to start talking about, similar to what we did in axial systems, right? We have indeterminate torsional systems, okay? What does that mean? Well, we have more unknowns than we have equations of equilibrium, right? In axial systems, we had some of the forces and some of the moments, right? We had 2 equations of equilibrium, usually. But now in torsional systems, right, we usually only have 1, right? Where some of the moments along the axis of our shaft. So we are going to talk about the process involved with, welcome. What'd you do?
Oh, I hurt some cartilage in my knee.
Ouch.
Yeah.
Are you done for the season, I assume?
Yeah.
Bummer. Didn't mean to rub it in. So what's the process here, right, if we have an indeterminate system? Well, first off, when we have an indeterminate system, right, we have our equations of equilibrium. And they do not provide enough equations to solve for unknowns, right? And in this case, we have some of the moments, right? That's what we get, some of the moments. So Any guesses of where we would start? What's the first thing we do in all of our mechanics problems? Free body diagram, exactly. Way to go. I need to bring candy or something. That was a big win. All right, so we do a free body diagram. Okay, in a free body diagram, we always assume coordinates, right? We provide our known forces on our system, right? Display our unknown forces in our system. And based on those unknown forces, we can use the equations of equilibrium, right? So assume coordinates. And we're going to find our expression for a sum of the moments equals 0, right? That is the only equation of equilibrium that we have in a torsional system, right? Because we're essentially summing the torques, right? A torque is a moment, right? All a torque is a moment about the longitudinal axis of our shaft. And so we only have that, right? We have no other forces acting on the shaft. Well, at this point, this is where we decide whether it's determinate or indeterminate. All of the problems that we've dealt with to date are determinate, okay? We've been either given what the extra loads are coming out of this, right? Or we only have one unknown force or torque, right? So we could calculate what that was. If we do not have that, similar to the axial systems, right, that we calculated that were indeterminate, right? Do you guys remember what that next step we did? Step 2. In axial systems, indeterminate axial systems. What's the next thing we did?
Set up a relationship.
Perfect. God, you're crushing it. Are you looking back at your old notes or what?
No.
Oh, damn it. Just a powerhouse over here. All right, determine, all right, how the system will deform. Right? Setting up those relationships, okay? And there's a lot of different ways that we could have a torsional system set up, right? Similar to the axial system. If I drew a little picture here. A shaft, and in that shaft we had a core. And say that shaft was fixed at one end, right? And we could apply a torque to the end of that, okay? So we have two materials. Say we had our first material and our second material, right? And those materials were inside of one another, right? So material 1 is inside material 2. They're connected inside that system, right? So if I rotate material 2, I'm going to rotate material 1, right? So if we wanted to determine the display or the rotation of material 1, it's going to be the same as material 2, right? So our relationship would say that our deformation of all members is equal. That means phi1 equals phi1, of course it does, phi2, right? phi1 equals phi2. Second one, well, in some cases we might, so this would what I would call a system in parallel, right? We have our two materials that are running within each other, okay? They're running together or in parallel. Sometimes we might have a torsional system similar to what we had with our axial systems, where we have a system of shafts in series, right? Maybe between two fixed plates. We might apply a torque, right? Within that system, right? Between the interface between our two materials. In this case, right, the total deformation is equal to 0. All right, now we have phi 1 plus phi 2 equals 0, right? Is really phi total. Because we have our fixed plates, right? This shaft doesn't rotate from one end to the other. So if we rotate, we run from our left-hand side to our right-hand side, right? We start at 0 rotation. This is a fixed support. Blue is going to say rotate clockwise. And then red, we're going to have to rotate back counterclockwise, right, to get back to the same spot as we were at the beginning, which is 0 rotation, right? Well, we've talked a bit about gears, right? Gear ratios and how those affect torque provided, how those can affect speed, right? And how that rotation can also be assumed between these two gears, right? Even though these gears are different sizes, the actual distance that are traveled, right, has to be the same. And so we can also reference, right, the rotation. If A rotates a certain amount, B's got to rotate a certain amount, and the amount of those rotations is subject to our gear ratio, right? So we can come up with what we would call angular relationships. Of deformation. Right? We know that A, because of our gear ratios, rotates proportionally to B via those gear ratios. Right? So those are our three big types of system deformation relationships, right? Some way of relating the deformation in one member or material to another, right? Because that's really what we're trying to do, is come up with this relationship that we can devise, right? A way to relate forces, right? Forces is what we're looking at. We want to relate force and deformation. In torsional systems, we call this the torque-twist relationship. Right, in the axial systems, we had this equation delta, right? Delta. Anybody remember what delta was? Right? We took Hooke's law, we took stress and strain relationships, we smashed them all together, and we got this equation that related deformation of an axial rod. FL over AE. Boom. Okay. Well, we also had something very similar to that in torsional systems, right? Where we figured out the angular rotation in radians. Right? You remember what that one was? It relates torque, geometric properties, right? And material properties. So we had torque times the length over the polar moment of inertia, right? Times the shear modulus, right? G, TL over JG. So in the axial systems, we took these this equation here, right? And we plugged it into this relationship, right? We're going to have some relationship that gives us, right, displacements in axial systems, rotations for torsional systems. So we take these V's and we just plug them back in up here, right? So we can get another equation. So step 4, we want to combine steps 2 and 3. so that the geometry of deformation is expressed using forces, right? So now we're going to have this new relationship or equation that has our unknown forces, right, our torques in there, relating the torque in one rod, right, or one material to another, which is very similar to what we have up here, right? When we sum moments, we get the relationship of torque in one rod or one material to another. And so now we're going to add, we essentially get another equation. So we can combine our steps so that geometry of deformation is expressed using forces. We call this the compatibility step. Because we were developing compatibility equations, essentially relating this deformation with forces. Right? And then finally, we can solve these systems of equations using our equilibrium equation, right? Here, we're trying to solve for torque, right? And once we have that torque, we can then solve for, shear stress, right, in our shafts, and so on. Okay, we're gonna go through an example. All right. So we have two shafts that extend, right, in series. So we got material 1 to material 2, extend between two fixed plates, and we're applying a torque at the center, right? The coupler between our two materials, right? They give us all sorts of fun information about this. They say that pipe 1 is made out of aluminum, okay? Pipe 2 is made out of steel, all right? So we have different shear moduluses for each of those, right? Steel, you can imagine, it's 80 gigapascals. It's stiffer than aluminum is at 26 gigapascals. The aluminum pipe, right, pipe 1 has a larger diameter than pipe 2, right? So we have a 140 millimeter pipe that runs to a 100 millimeter pipe. And then we have thicknesses of our walls, right, of our pipes. And we have different lengths, okay? And they tell us what the value of our concentrated torque is, right, kilonewton meters. And they want us to determine a number of things, right? They want us to determine what's the maximum shear stress in each of the pipes, okay? Well, as we just found, right, we have an equation for the maximum shear stress. We need the polar moment of inertia, and we need the max radius, and we can get that out of our dimensional stuff they gave us, right? The max diameter and the wall thickness. And then we can figure out, right, we need to figure out what the torque is, right? That's something we do not know. Next one, what's the rotation angle of flange B relative to support A, right? So really they just want us to calculate, well, what is phi for rod 1 for FL, right, over JG. So we can figure that out. So we have one equation of equilibrium. We're going to start there, right? We're going to start with a free body diagram. Right? Step 1, we have our free body diagram. I am going to cut, right? We need to figure out internal forces. It probably wouldn't make much sense if we drew a free body diagram to the end, right? That really doesn't encapsulate our applied torque, right? The center, okay? It doesn't have or show us any forces that'll let us know, like calculate known forces, right? Or unknown forces. We missed the boat on figuring out what the torque is in rod 2, right? Which they asked us for the shear stress. So I am going to, instead of doing that, I'm going to cut out the center of this torsional system. Right? We have, I capture my applied torque, right? And I'm able to display internal torques in both rods 1 and rod 2. So we're going to start by, I'm going to say that's the coupler. We have our 2 rods. We need a coordinate axes, right? So I'm going to walk through, right? Now transferring known and unknown forces, in this case torques, right, to this free body diagram. So if I look at the applied torque at 15 kilonewton meters, right, or TB, if I use the right-hand rule, right, and I cut this, so this is rod 1 and rod 2. So this x-axis is the same as that one. So if I curl my fingers in the direction of torque B, right, my thumb's pointing off to the right. So at that coupler, we're going to get the torque at B, right? It's acting to the right. The forces in rods 1 and 2, I have no idea what they are, right? So I can just assume some directions. I'm going to assume some positive directions. So I'm going to assume T2 acts in the positive x direction. And when I say I'm assuming positive, I'm going to say that they're outward normal, right? So T2, positive x direction. I'm just going to set T1 equal to the opposite direction. Just like that, okay? You could assume them in any direction, okay? Right, this is up to you. And the math will tell you which direction it's landing. So we have one equation of equilibrium, right? Sum of the moments about our x-axis, right? Torques are just moments, so I'm going to sum moments about that axis. Set it equal to 0. Well, in this case, we have torque B plus we have torque 2 minus torque 1, right? And that's all just based off of the direction that I assumed those blue arrows to head, right? T1 and T2. TB, we know, acts into the right direction, or positive direction. So based on this, it's indeterminate to the first degree, right? We have one additional unknown beyond our equation of equilibrium, right? One equation, 2 unknowns, first degree, okay? As was outlined in our process for indeterminate, right? This is where we start setting up our relationships, right? We need to assess the deformation. Let's assess the deformation. Out of our 3 different, right, torsional system types, what can we say about the deformation in our 2 materials? 2, 0, right? Exactly. Because we have 2 fixed ends, and if we travel through our system, right, from the left-hand side at A to the right-hand side at C, we're going to start at 0 rotation, right? We're going to twist a little in rod 1, then we're going to twist a little in rod 2, but we got to come back to the exact same orientation we were at the beginning, right? They're both fixed. They don't rotate. So we can say that our total rotation is 0, and that rotation, when we move from the left-hand side to the right-hand side of this shaft, phi1 plus phi2 has to equal 0, okay? Now we get to relate our, oh, this is 3. We want to relate our force deformation, right, or torque twist relationships. Well, we know phi1 is just going to be the torque in 1, the length of 1, the polar moment of inertia of 1, and the shear modulus of 1. We also know that the rotation of 2 is going to be the torque at 2, the length at 2, the polar moment of inertia of 2, and the shear modulus of 2. We can take those and plug those into that upper equation, right? We're just going to say 0 equals d1L over jg of 1 and TLJ plus TLJG of 2. So out of this equation, though, right, we know a lot of things, right? We know L, we know J, we know G for each of our 2 bars, right? They gave us the length. They gave us the shear modulus because we know its material is aluminum and steel. And then finally, the polar moment of inertia, we're going to know that based on the dimensions of our pipes, right? In our case, rod 1 had an outside diameter, right? Our big D equal to 140 millimeters. For pipe 2, it was 100 millimeters. We know the thickness for the second pipe, or the steel pipe, right, was 6 millimeters. And they gave us that the thickness of our aluminum pipe was 7 millimeters. Well, we know the polar moment of inertia based on our notes, right? And based on our diameters, we can say that the polar moment of inertia is pi over 32 outside diameter to the 4th minus the inside diameter to the 4th. All right, this would be outside, this would be inside. Well, if we did that for number 1, right, so we take 140 millimeters, we subtract 14 millimeters, right, to get the inside diameter. We could plug those values in. We get 12.97 times 10 to the 6th millimeters to the 4th. J2, we do that same process, right? We do pi over 32 outside diameter to the 4th minus the inside diameter to the 4th. And we end up with 3.93 times 10 to the 6th millimeters to the 4th, right? What does this tell us? Okay? This tells us that there's a difference in stiffness between the 2 pipes with respect to rotation, right? Moment of inertia, as you guys are working in the homework or have already worked in the homework, right? Moment of inertia from statics, right, is the resistance of a cross section to bending, right? Rotation. So it'd be like this I shape, twisting this way and twisting this way. J, on the other hand, is how resistive is your cross section to rotation about the longitudinal axis, right? If this beam kept going, it's really long, right? Rotation. So what does that tell us? Well, intuitively, I would imagine if I took a pipe with a larger diameter, maybe it was 4 inches in diameter, and I tried to twist it, it'd be harder to twist, right? It'd be stiffer than it would if you took a 2-inch diameter pipe and did the exact same thing, right? So that's what this is saying. So what this tells us is that the aluminum pipe, which is 140 millimeters in diameter, is nearly 3 times, it's a little over 3 times, right, as stiff as the pipe that's 100 millimeters, right? Which makes sense. Something to think about when you're going through homeworks, right? And any problem, right? You want to validate it in some sense. You want to step back and think, does that make sense? It does make sense, right? Stiffness is based on geometry, right, with respect to diameters. Okay. So next, right, the idea is we have this torque twist relationship, and we can then plug that value into our deformation assessment that we made, right? So step 4 was to combine steps 2 and 3. So now we get this equation that says we have 0 rotation from one end to the other end of our system. And that rotation is going to be the sum of the rotation of the first shaft, right? Plus the rotation of the second shaft. So we end up getting T1, L1, J1, G1 plus T2, L2, J2, G2, right? Well, we really want to take something out of this equation. Now we have two equations, two unknowns, right? We have L, we have J, we have G for both of our two members, 1 and 2. Two unknowns in this equation are T1 and T2. Well, the two unknowns in our equilibrium equation are T1 and T2. Right? Two equations, two unknowns. We solve that by manipulating one equation in terms of one of the forces and then taking that and plugging it into the other one. So what am I going to do? I'm going to manipulate these equations here to get us an equation for, say, T1 or T2. In my case, I'm going to do T1. So if we rearrange this for T1, we get that T1 is negative T2, L2 over L1, J1 over J2, G1 over G2. Right? Right? If we take all of those values, right, we have L2, L1, J1, J2, G1, G2, right? We can plug everything in and come up with an expression for T1 equals 0.894 T2, right? Well, now that we have this expression, we take the expression we have for one force in terms of another, and we plug it into our original equilibrium equation, right? And then we can solve for our unknown forces, right? So 5 is we want to solve our equilibrium equation. What does that look like? Well, we have sum of the moments about x. We set that equal to 0. We said it was TB plus T2 minus T1, or TB equals T1 minus T2. That all equals TB, which was 15 kilonewton meters. All right. Plug in our relationship between T1 and T2, right? So now we're just going to have, so we have 15 kilonewton meters. T1 we know is negative 0.894 T2 minus T2. We get T2 equal to negative 7.92 kilonewton meters. And if we plug, right, this back into there, we're going to get T1 equal to 7.063 kilonewton meters. Right. Which is interesting because at the beginning when we were calculating J, right, I said that the steel pipe was about a quarter of the stiffness, right, or a third of the stiffness of the aluminum pipe. But the fact that our modulus, our shear modulus, is so much larger for our steel pipe than our aluminum pipe, right? Our steel pipe ends up, which is T2, ends up taking more torque out of that system than our aluminum pipe does, right? So material ends up playing a big role in how forces are distributed, right? So we have T1 and T2. They asked us for what is the maximum shear stress. Well, now at this point, things become pretty simple, right? And fairly trivial. We just take our known values now, right? We have the max radius, we have the polar moment of inertia, Now we have the torque supplied. We can use our torque stress relationship, which is this, rearrange it for tau max. We end up with, right, the torque times the max radius over the polar moment of inertia gives us our maximum shear stress. We can plug that in for each of our pipes. So we got the maximum shear stress in our aluminum pipe, or pipe 1, is going to be the torque at 1, the max radius of 1 over the polar moment of inertia of 1. Make sure we watch our units. I'm going to have mine come out in megapascals, right? Or newtons per millimeter squared. Our second is going to be 100.8 megapascals. Right. Our steel shaft, even though it was smaller in diameter, right, and thickness, our shear modulus, right, was 80, right? It's about 2.5 times as stiff with respect to our shear modulus, right? Our material properties. So we got more torque, right? We had more torque. Well, now that we have more torque in our steel member, right? Our maximum radius is smaller, our polar moment of inertia is smaller, so now our stress, right, is larger. Yes.
To get those stress maxes and G's, you just plugged in stuff in that equation and that's what.
Yep. Yep. So this would be, tau max of 1 is the torque in 1 times the maximum radius of 1 over the polar moment of inertia of the 1.
Maximum radius for the outside.
Outside diameter, right? All the way to the outside. Even with a pipe, we're looking at what's going on the very outside of our pipe shell, which is the maximum radius, right? All the way out. Part B, they asked us for phi, right? The angle of rotation. Again, we have everything now, so these are pretty trivial, right? T, L over J, G. So if we do the same thing, right? We want to make sure we watch units because this is in radians or unitless. So we want to make sure if this is in kilonewton meters, right? The rest of our stuff is either in meters, right? Or newtons or kilonewtons, right? All of those things to make sure everything is balancing top and bottom, right? So in this case, if we plugged everything in, we get 0.89 radians for pipe 1, and we get negative 0.189 radians for pipe 2, which if we go back to our deformation relationship, right, we said originally that the rotation of 1 plus the rotation of 2 equals 0. And plugging in our values, we get that. Right? Questions? Fairly involved. Right? All right, we just finished up what we should have finished up about a week and a half ago. All right, congrats. You did it. Woo. All right, so that's torsion. Yeah, we should clap now. Clap now. I almost thought about clapping when you fell asleep. You guys ever done that in the class? Somebody falls asleep, you get everybody else in the class to start clapping, and then when that person wakes up because everyone's clapping, they just start clapping. It's early. I get it. It's early. Or you just get everybody to leave the classroom. I've done that also. All right. So be careful. Don't fall asleep. All right. This stuff is riveting, right? You shouldn't fall asleep. All right. So now we're going to step into stress concentrations and combined loading, right? So we have axial loads, right? We've gone over axial loads. We've gone over torsional loads, right? So So now we can look at systems. The real world is more complicated than these very rudimentary, simple systems where all we either going to have is axial load or torsional load, right? And we're going to end up working on bending. And so we're going to end up having all three. But we're going to step through adding both of them together. Before we do that, though, I wanted to step back, and with respect to axial loading and torsional loading, right? We initially talked about this idea of St. Venant's principle, or the idea that, right, if you had a column, right, so we had this column, and I put a point load on it, right, or just look at the whole box lectern here, or whatever you would call this thing. I think this is for an old projector, right? So you set this here, right, and I put my fist down and I put a load on this, right? The top sheet of this thing sees my fist as a very concentrated load, right? Right at the very surface of the box up here, right? As we start moving further and further away, what St. Venant found is that once you get, right, width was 2 feet. Once you get 2 feet down into this member, right, it doesn't really care about my fist anymore. Everything becomes uniform. It starts smearing out, right? It becomes uniform. And this is what we've been looking at to date in this class. It's just assuming that if we pull on something, right, it becomes uniform with relatively quickly, especially with respect to the problems we've been looking at, because we're not looking at a column or an axial member that's like 2 feet square. We're looking at something that might be like a couple inches square, right? So when you have something a couple inches square, you only get 2 inches down, and that rod no longer cares about how it's being connected and that force is applied. It's going to assume that that force becomes uniform, okay? That makes sense? So, well, I guess a couple things here first. Stress concentrations, we're going to talk about chapter 5.2, 5.7, and 6.10. That's the torsional. So we're going to start in the axial chapter, which is in chapter 5. And like I said, this is St. Venant's principle. And the big thing to take away is that in systems, right? So if you're any and you were looking at, say, the roll cage on a go-kart or something like that, right? And you have axial demands on those pipes and things and connections between them, right? Relatively quickly, those pipes start seeing just a big uniform load, right? Okay. But if we were to look at very small, right, changes in geometry, right at that change in geometry, we end up getting what we call stress concentrations. Okay? And those stress concentrations exist because what we end up having is what we call these are called stress trajectories. Right? They are parallel to our max normal stress. So we're essentially taking this nice uniform, right, stress orientation in our cross section, and now we abruptly are changing the geometry. Okay, so now we take all of those stress that stress that used to have the whole cross section to travel along, and now we got to go through a notch, right? We've got to take those stresses that were nice and uniform on one side or the other, and we got to squeeze them through, right? Or squeeze them around, right? Or have them go from a small width to a larger width, or vice versa, right? So what squeezing those stresses does is, right, we're reducing geometry, we're changing the cross section, and so we end up spiking or increasing the stresses around those discontinuities, we call them, okay? So we end up with concentrations at interruptions to our stress path. So if we looked at the normal stress, right, as we try and smash this nice uniform stress path, right, these trajectories, when we start to smash them through a smaller cross section or around a hole, we end up getting spikes in our normal stress. We get spikes in our normal stress, right? So we have notches, we have holes. We call these shoulder fillets. Right? And it's hard to get away from these, right? There's a lot of things that make us want to change geometry, put notches in things. Everything's not just going to be the same uniform shape, right? We have to connect things together. Right? Bolts are a very nice way to do that. We might want impose design efficiencies. Right? We might need more material at a certain location, but then that material, right, as we continue along its path in the system, we might not need all of that material, right? So we want to neck that down. We don't want to use as much material or size of our pipes and whatnot. So we want to impose some design efficiencies. And the system might require it. Right? The system that we're designing, the application of whatever we're designing it for, might require some changes in geometry along the way, right, to accommodate its intended purpose. And so we're going to need to start looking at these stress concentrations. How are we doing it in this class? Well, we're doing it very easily in this class, okay? We are, okay? Not in a bad way, okay? Engineers are very lazy, as I've mentioned many times before, right? If we don't like to redo something, if someone else has already done it for us, okay? So in this class, what we're gonna end up doing is using very basic, okay, graphs that allow us to essentially go out and figure out a factor that we would impose upon our stresses that we would normally calculate, right, at a given location, and be able to relate those stresses to what are the maximum stresses, right, the stress concentration. So we amplify with this stress concentration factor our normal stresses, right, so that we can figure out, well, what is the spike, right, or the peak of these stresses as we go through these changes in geometry. Right? So the easiest way is just through these graphs. So, right, if we had this big uniform tensile stress over this plate, right, we put a hole in the center of it, right, in order to move that stress, we end up getting a series of not only normal stresses, but we end up with shear stresses. We'll learn more about that here soon. Okay, so we get stress redistribution and movement, right? Creates normal and shear stresses around the perimeter of our hole. It's already 8:50 every time. It just creeps up on me, right? All right, don't forget homework, okay? By the end of the day tomorrow, that's 5 p.m., not midnight. Like I said, I'll be sending out an additional homework. It'll be due the end of next week.